let's take this application that we're looking at, and let's have it use PARALLEL-NETCDF. And you'll hear a lot about another data model library after lunch when Gerard Heber from HDF talks about their data model library. I gave them 2 hours because HDF5 has 300 function calls and a really elaborate interface. PARALLEL-NETCDF is a much simpler interface that has pluses and minuses, but it does map really well to the kind of game of life data model, and it maps really well to the climate data model, and it maps well to other models as well, if you're doing multidimensional arrays, which work out a lot in quite a few application domains. I'll keep showing this probably half a dozen more times today, just so you remember where we are in the software abstraction forest. We're going to talk a lot more about this upper layer here. We have a I/O library that will help bridge the gap between these low-level bits and bytes details of the middle layer and speak more in a language that is familiar to an application person. Speaking in terms of multidimensional arrays, say. And so that has a couple different advantages. One, not only is the interface more suited to what application developers are going to do, the back-end storage is going to also match up a lot. We'll keep the details of where these arrays are stored in data, what's going on, how are they managed in the back end. For example, HDF5 is going to take this multidimensional array and chunk it up into pieces and maybe compress those pieces or put some kind of filter on them and reorder them. But to the application, it's just going to give me the 10 by 100th element of this array, and the details are hidden. And the important part that these libraries introduce, and this was really important when we had BlueJeans show up, is the idea of a portable file format. Now, nobody here has a Spark book or an Alpha laptop. We all have x86 processors on our table right now. And when you write a file on an x86 processor and you read it somewhere else, no problems. It's all going to be 32-bit ints, 64-bit longs, and 64-bit pointers. BlueJeans showed up, and all of a sudden a big endian machine appeared, and then people were like, "What's going on? I've never dealt with a big endian machine because Intel's everywhere." Well, the file formats, if you're using PARALLEL-NETCDF or HDF5, that was no big deal. We just took the file from BlueJeans, put it on your laptop, and the conversion happened behind the scenes. Byte swapping is not a big deal, but it's an extra step, extra headache. So Phil showed this slide, but I'll just reiterate, because we're looking now about what's going on inside PARALLEL-NETCDF. Again, you have got a climate code that's modeling the surface of North America, and you'll have an atmosphere chunk of atmosphere. It's got latitude, longitude, and altitude. Or maybe you've got a patch of the continent, and you want to know the barometric pressure at sea level. None of that on this left side has anything to do with give me the 10th cylinder of the 100th hard drive. No, we're talking about science data here. So that all wraps up into a sort of a structure where we can describe with annotations the units, the actual, we can hide from the user, but we document the starting offset in the file, and we annotate the type of the data and the size of the data, and there's a human readable name. It's not going to be 0x355, it's going to be called temperature. Similarly for pressure. And then NetCDF will store all the temperature data and all the pressure data, so on and so forth, one after the other. And this is great in lots of ways because after we've created the header, we can programmatically figure out where every byte of every array is. There's no need to do any coordination or synchronization. Now the trade-off is you have to be able to declare ahead of time all of your variables, but for a lot of workloads, that's not so bad. We can slot PARALLEL-NetCDF right into an I/O stack and not care whether it's the Argonne Romeo implementation of MPI/I/O or IBM implementation, back when they had their own implementation, right into GPFS. PARALLEL-NetCDF is going to make standard MPI calls. It's going to do the type creation and the collective calls, and you don't have to worry about whether you're dealing with platform X or platform Y. There are a lot of similarities between what we call Unidata or serial NetCDF. This was an easier distinction to make until a few years ago when the serial NetCDF people added parallel interfaces to them. So now we have Unidata serial NetCDF, Unidata parallel NetCDF, and then Argonne Northwestern parallel NetCDF. But we'll just try our best to keep the three different cases as clear as possible. And so we'll see them used a lot in climate, a little bit in the fusion communities too, and astrophysics. I'll just tell a story here. I've got some time. The fun part about working on Parallel NetCDF in the beginning was we had these friends at the University of Chicago, the Flash group, that they used HDF5 for a long time. They were writing checkpoints with HDF5, and it was doing fine. They didn't know any better. Then we wrote Parallel NetCDF and convinced them they should give it a shot. And the friends at the Flash group are astrophysicists, but they're very pragmatic, and they'll try anything out. They've got the abstraction layers. They can drop a new I/O library in, no problem. And they got 10 times better I/O with Parallel NetCDF. And then our friends at HDF5 scrambled real fast and like, oh no, we can fix that. You just have to tune this and this. And then they were doing better than Parallel NetCDF for a while. And then Parallel NetCDF came along and okay, well we'll do this interface and then we can. Anyway, it was a friendly collaboration between HDF and Parallel NetCDF. And so anyway, that's why the fusion community is using it. It's an extra, I guess they might call it a risk mitigation strategy, but it helps keep both libraries honest. It's great when that happens. We had a chance to experiment a little bit there. So let's take the game of life model and map it into Parallel NetCDF. Not too bad a fit. This array, this global array, looks like a Parallel NetCDF 2D array, no problem. And then we have this little iteration. Okay, so the array describes its x's and y's dimensions. That's part of the description of a NetCDF variable. The iteration part doesn't fit as part of the array, but we're allowed to do these things called attributes, putting annotations on the file. And you can do all kinds of things with these. They're strings, integers, doubles, whatever. And you can annotate the data set itself or specific variables. In this case, we'll just attach the iteration as an attribute to the variable. So you should remember the checkpoint interface, so still keeping the same, maintaining the same outward-looking interface, taking a file location and a chunk of memory and a description, and then we'll do some NetCDF with that. Creating a file in Parallel NetCDF looks a little bit like creating a file in MPI. You give it a communicator, you give it some tuning parameters and an info, an access mode and some tuning info, and then you get back an identifier. And this identifier will be associated with this communicator and file name, and that's all you'll worry about from there on. Again, this is collective. Everybody creates the file, and once you do that, once you create the file, you're in what's called define mode, and I'll talk more about that in a bit, because this bimodal nature of Parallel NetCDF is what is both restrictive and helpful for it. Before I get there, we're going to talk a bit about some of the descriptions. Parallel NetCDF has one way of describing data, multidimensional files on disk. So you have a variable identifier, and you give a starting location in that array and a count in X, Y, and Z. And this subarray access is one of the more common ways people call Parallel NetCDF. There's a family of put routines and get routines, but we'll focus on the subarray one. That's the most natural fit here. We can also use MPI data types to describe in memory what's going on. In this case, it's just a subarray, but you could imagine any kind of structure in memory, of trees or irregular shapes or anything. As long as you can, in your program, think of a way to map that to a multidimensional array, then you're in good shape. As applications get more sophisticated and they start using adaptive mesh codes or unstructured grid codes, the NetCDF multidimensional array model is a less good fit. However, it's such a good fit for I/O that we haven't come up with anything better. To come up with a truly flexible and handle everything unstructured grid library that does I/O efficiently, that's been a bit of a challenge. So we're still asking applications who know their code best to come up with a way of converting whatever they have into these multidimensional arrays. So if you're an application person, sorry, we tried and we couldn't come up with anything better yet. We'll still work on it. Just remind us where we were in the code. we're creating the file, and now we're going to, everything up to this code, this line here, end define mode, is a description of the data. We define dimensions. We have a row and a column dimension. We'll define a variable called matrix, you'd call life, whatever you want to call it. And we associate a data type with that variable, in this case integers, with these two dimensions. So we have an array of dimensions, we have a type, and that's your type. That's your NetCDF variable. It has a name, a type, and dimensions. And after we exit define mode, then we in what's called data mode. Now the library knows everything that's going to happen in data mode. When you describe your memory type and then put that data into the file, the library has saved on every process the state of that header and knows where the objects are going to go, and everything's hunky-dory. Now we have a little bit of a local state. We're converting from the global notions to the local notions here, and then put the data collectively. Okay, so we'll walk through this here. It's a parallel NetCDF call. We're writing data. We're writing a subarray data collectively, and we're taking all the data associated with this variable identifier. We're giving it a location in the parallel NetCDF file, and then we're giving it with MPI bottom, count, and type a description of our memory structures as an application. Then we close the file. Now that's all there is to it. There's no need to worry about sending data to anybody else, receiving data from anybody else. We're just going to write the data out. Restarting is a little simpler. In this case, we're going to make some assumptions to simplify the code a bit, but you could come into this checkpoint file knowing nothing other than you could even not know it was an NetCDF file. And then you can query it. You can use these routines to understand how the data is laid out and then do the right thing. So again, we locally figure out where we are, turning the global state into local state based on my number of processes all together and my rank. Then we figure out what file we're going to open up. We, again, same thing as create, only instead of calling it create, we call it open. We get a communicator and a name, and we get an identifier here with this NCID. The interrogation routines look like this. They're all called inquire, and in this case, here's an example where we, given this NetCDF file and this dimension identifier, we want to figure out how big is this, how many columns are in this dimension. And we can do this for all the different aspects of the file. We'll see this a couple of cases in this session. And now we don't have to worry about being careful about whether this blob of data on the file is exactly what we are expecting. We can look at it and figure out, okay, well, I'm expecting an X by Y global array. Great, I've got that here. As you can see, we can inquire that and then either adjust our behavior or alert the user, hey, you didn't get the right configuration. If you're just you could feed a MPIO checkpoint restore code anything, and it would just plow through and give you garbage data. There would be really no way of telling if the data in an MPIO formatted file met the conventions that you were expecting, except by looking at the garbage data, I guess. So again, we're going to we're going to figure out what the variable, and then once you have the variable identifier, you can get the dimension identifiers, and once you get the dimension identifiers, you can get the length of the dimensions. And so step by step, you can break down, and you can, in fact, it's even more general than that. You can omit this var ID part. You can just call ncmpi inc with a bunch of enough arguments, and it'll tell you, hey, you've got 2 global attributes, 10 variables, and 5 dimensions. Dimensions are shared among variables, so that's why there might be different numbers of things there. And I'll show you an example of that later on. So once you've done all the inquiries and figured out the file, we can then, like we did before, do an all reduce and check to make sure that everything is what we expect. Did everybody, first we'll do some memory allocation based on what we figured out from the file, and then if everyone had any problems allocating, we will give up early or we'll just continue on. Now again, we're able to turn our global view into local views with these offset columns and rows, And now once you have this start and count array populated, we can do a collective call, fill in the data, and then update the matrix array with the data we just read. This buff array is going to be a contiguous chunk of data, and then we'll pile it into the, we'll populate the matrix array the way we need to. So here, this is an example of the conversion between the NetCDF multidimensional array format and the user's data model. In this case, it's a good fit, so there's not much to do other than simple assignment. So we were able to do our I/O thinking about not just the low-level storage ideas, but thinking more in terms of arrays, data types, and we can annotate the data with these attributes. And then now when we hand that data set to somebody else, they can figure out what it is. They don't have to know ahead of time what the convention on this file is or how the file is structured. And then all the optimizations that happen in the MPI I/O library, whether it's data shipping in the old IBM interface or data sieving or two-phase in Romeo, happens behind the scenes. And for you as an application person, there's no worries there. So now that we've looked at how this game of life example might use PARALLEL-NETCDF, we'll talk a little bit more about PARALLEL-NETCDF itself. I guess we're coming about it sort of sideways, right? We've looked at a real application making PARALLEL-NETCDF calls, and now we'll talk some more about the library, all the other features the library has to offer. Now, I talk about PARALLEL-NETCDF a lot, and the mailing list hosted at Argonne, but my collaborators at Northwestern, Wei King and Alok Chaudhary and Kuei Gao, who did a lot of work a while back before he went on in the industry. Anyway, Northwestern is an equal, if not more, partner on PARALLEL-NETCDF. I want to make it very clear that Argonne is only one party here. Northwestern is also very active in PARALLEL-NETCDF. So I showed you already how we mapped from fixed width variables into a file. You can compute the X, Y, and Z, and then you know the offset. There's another kind of variable called a record variable in PARALLEL-NETCDF. And you can imagine using a record variable in the cases where you are, say, sampling a temperature sensor every 5 minutes or something for indefinitely. And so you're going to record that data at the end of a variable. And this is the part in PARALLEL-NETCDF where maybe we as computer scientists didn't quite understand the importance of record variables. We figured, well, record variables are hard. It's a challenging workload because if you have several record variables, they end up interleaved like cards or something like you might imagine. And so that creates a non-contiguous access, and well, that's a bad idea. We'll just tell people don't use record variables. Well, of course, the whole point of these libraries is to meet the application writers where they are, and everybody uses record variables. So that requires some tuning, and it might, if you use PARALLEL-NETCDF and get bad performance, record variables might be part of it. And we've got some approaches to get to fix that. But talked a bit about this define mode and data mode already, but it's nice. It's a nice aspect of the library because we're able to have rank 0 do all of the updating of the file. It's a very small header relative to the rest of the file. And then everybody else has a cache of it locally. And it's illegal in PARALLEL-NETCDF and serial-NetCDF to have one process define a variable, another process define a different variable. If you do that, you'll get, they'll compare notes at some point and say, whoa, the header is different here. I can't continue, there's too much changing. And what happens, early on when people were using PARALLEL-NetCDF, one of the things you would store as an attribute is a timestamp, right? I'm dumping this checkpoint on August 11th, 2016 at 11:55 and 25 seconds, right? You can get really precise, but with 1,000 processes, some people might be off by a little bit, and so we get some bug reports that people are saying, what's going on here? It tells me the header is different, and it would turn out that timestamps were one of those things. We've relaxed that a little bit for attributes, say. But we can't relax it too much, or else you'd have this problem where everyone's unsure of where data lies. And then because rank 0 has all the information, but it's the same as everybody else, we'll write out to the file. I know I just got done saying we want to do parallel I/O everywhere, but in this case, the header is really only a few kilobytes, and to do a parallel write of a few kilobytes would just be overkill. You'll get better performance there. I guess with all these things, you have a scale of where it pays off and where it doesn't. So here's a case where one serial operation is fine. And that's the last time we have to do anything to the header. Once we exit define mode, that header is fixed until we re-enter define mode, which is a really expensive operation in PARALLEL-NETCDF, so try not to do that. Data mode is where all the magic happens, right? We put each variable into the file. Under the hood, we're calling MPI file set view to describe where in the NetCDF, in the PARALLEL-NETCDF data set where we are. We are going to talk about, and then the collective call. After you do all that setup and bookkeeping, then the collective call uses all those optimizations and transformations we talked about in the first half of the day. And then the MPI-O layer might do those things, and then the parallel file system, if the MPI-O layer is tuned to that file system, maybe has some special features. So right, we're working all the way down through the stack, and each layer maybe using optimizations to get things going faster. I like this timeline view. You probably saw something similar in the MPI tutorial. It's getting a little long in the tooth these days, but it still does a good job of showing what's going on and capturing all the different layers of the stack. So we start up in the corner here. In this pink is where we did a collective file open. All these processes. This ran on Blue Gene, a very small scale process on Blue Gene. Everybody opened the file. It's collective. Okay, great. You can barely see it, but there's a tiny little sliver here where one process did the independent write of the header data. And then this is a flash astrophysics checkpoint. They're going to write out some grid or AMR data here. That's several small variables. And then there are, in this case, 3 larger variables. And of course, you see some processes are taking a long time to write, and some processes are taking almost no time at all to write. What's going on with process 0, 4, and 8? Well, those are the I/O aggregators. Those are the actual processes that are collecting data and doing the actual I/O. But because each of these operations is a collective operation, we end up, what do I want to say here? Yeah, so every process enters MPI file write all, and the ones that have no data have to sort of hang out and wait until they've sent their data off to the right process. But then, as you can see here, once you've done that, you can return and enter the next call. This is the file close, which again is collective, so there's a little bit of coordination that has to happen there. But in this case, it's collective but not synchronizing. So you can end up with a case where some of these processes are taking a little while to wrap up. But on Blue Gene, that was great. We had fewer processes doing I/O. Anyway, this is just a peek under the hood of what's going on. Right, I should tell you that even though this says inside PARALLEL-NETCDF, these are actually the MPI calls being made. If you were to wrap these bars on the timeline with PARALLEL-NETCDF calls, it's basically a one-to-one mapping. The MPI the file open is basically NCMPI create with a couple extra little lines of code. And each collective write here is basically an NCMPI put var all. So it really wouldn't be very interesting if you also annotated this with the PARALLEL-NETCDF calls. It would look basically exactly the same. So I talked a little bit about how the collective operations happen one after the other, and how we have cases where maybe you're not always in a situation where that makes sense. So we can decouple the description of data with the execution of data and do that in what looks like a non-blocking interface. It's not asynchronous. I want to be clear that nothing actually happens in this description and this data other than in these series of calls. Nothing's actually happening until you get to this green line where you actually wait. So let me step back here. Consider a simple application where you have a variable in purple and a variable in orange, and you want to write that out to the file. You could do 2 operations, or we could stitch them both together and do that in a single operation. However, PARALLEL-NETCDF is very array, and serial-NetCDF, very array, or very variable-oriented, and so you can't issue a single function call that says, write all this data in one call. But what you can do, and we do it with this this non-blocking interface is say to the library, here's a description of something I want to have happen. I want you to put this data in this file, and let me know when it's done. And now here's another description of something I want you to do. And once you've done all that, once you as the application writer have written out all these requests, and they're very fast, right? All you're doing is registering a request to the library. You then wait for the application. So in this case, that's when the actual I/O happens. That's when you take all these requests and blast it out to the file system. And the nice thing about this is you still have the same buffer reuse rules that you have in MPI. We can't touch the buffer until you're done. But if you're okay with that, if you can sort of give this memory over to the NetCDF library, then the NetCDF library will take care of stitching up both these requests into one larger, hairier data type, issuing one larger, hairier collective I/O request, and you'll get much better performance. And we did this a while back for our friends at the Flash group. I've mentioned them already, but I'll talk a little bit more specifically about what the Flash code is doing. They are going to detonate a star, and then they want to, as it evolves, as that explosion happens, they want to be able to capture it and then later visualize it somewhere else. So you don't get this pretty picture on BlueGene. Instead, what you get on BlueGene is a bunch of checkpoint or plot files, and then somebody else renders those and visualizes them. So they really want to have frequent checkpoints so that they can create these sort of step-by-step animations. They want a canonical format because they need their visualization and analysis team to be able to look at the data and produce something that's more human-friendly. And again, like the game of life example, they have certain structure in the adaptive mesh that they don't want to capture in the file. Instead, they want to canonicalize out to the file. And so they're going to discard any ghost cells. In this example, sometimes there's each experiment, each simulation they run on BlueGene could have a variable number of variables. Maybe it's 10, maybe it's 23. Depends on the simulation that you're trying to run. But if you issue an I/O request for each one of these variables, you have to pay the synchronization costs at each time. You're not able to give the storage system as much description as you were before, and you end up with a fairly unimpressive amount of data. But if you were to use this non-blocking I/O, sorry, I shouldn't say non-blocking, I should say the write combining optimization, where you've issued a write request for every one of the variables, and then you say, okay, go ahead, fire it off. You get a much bigger jump in performance. And this works out really well for Flash, even though they have regular checkpoint times. But this optimization also works out really well for this Chombo example like I was talking about earlier. I wish I had a better slide for that, but I just thought of it now. As you are walking down the tree, you will tell the library, here, this is what I want you to write when I'm finished walking everything. And then everybody descends the tree and says, go. And then you get a huge jump in performance because now you can, instead of dealing with independent requests, you can coordinate and optimize and do all the other things that are important. We did this, our friends of the astrophysics, the cosmology code called HACC, also looked at using PARALLEL-NETCDF. And it's a fun case because instead of dealing with arrays, you're dealing with particles, although the particles are traveling in what's kind of an array, it's just a universe-sized array. So the way this works, right? You start off with some number of particles, you simulate the Big Bang, and then you run your simulation for 13 trillion years, and you see how it looks in the simulation, and then you look at the sky, and you say, okay, that's pretty close. Okay, I guess I did all right. My math is good, my gravity models are correct, and everything's fine. And in the first simulations, it was something like 217 particles, but now we're dealing with 13 trillion particles, sorry, not 13 trillion particles, 13 billion years, about a billion particles, maybe even more than that. But we're getting more and more particles, and they interact with each other, they clump into galaxies, they blow up in black holes. And so you end up with, for each particle, you have certain field math, and this is all parts that happens in the application part. But the I/O part wants to capture all the particles where they are so that you can restore your simulation, right? Running for 13 billion simulated years requires a few days of computer time, a few calendar days of time. So they'll run for a few billion years, and then they'll restore from a checkpoint because they either ran out of time on their allocation or the storage crashed. Or these guys are great at finding corner cases on our supercomputers, so they get a lot of early access to them. But they checkpoint too, so they don't lose science. They can actually get their science done while beating up on these machines. If you're going to capture the HACC particle data in PARALLEL-NETCDF, you might describe with a bit of experiment information, some of the size of your particles that you're using and how many time steps are going on in your metadata, in your annotations. And you might keep a big giant array of an index, which says, this particle n, and there's, again, a billion or more particles, is going to live in this boundary and it has a start and an end. And then, sorry, let me back up. We have blocks, right? We take the universe and we decompose it processor by processor into some of these arrays. And so you have your table of particles over here, and that's clumped up into blocks. So, you might find as you consult this list of particles that 1,000 of them are in block 1, and 2 of them are in block 3, and 0 of them are in block 4, so on and so forth. So even though PARALLEL-NETCDF isn't a universe storing data set, it's a multidimensional array storing data set, with a little bit of thinking you can come up with a schema that makes sense for PARALLEL-NETCDF. So how does that look in the HACC code? HACC is a C++ code, but they make all the C codes that PARALLEL-NETCDF is providing a C interface here. So you'll see things like a constructor that creates the file. And in this case, we're using an extension to the file format so that we can describe 2 billion or more elements in the file. We have some attributes on the file. We're describing the dataset itself with NC global. We're not going to describe, we can also describe specific variables. But we'll put a text attribute here. We'll put some floating point values, again, on the whole file. And then after we've described the metadata, the provenance of how this file was created, we'll start describing the structure of the data. We have some dimensions we're going to define, the index, an array of keys here. Again, here's an attribute we're going to put on the key index variable, the scalar variable. There's no notion of units in PARALLEL-NETCDF, but lots of applications use these conventions. So they'll say this is kilometers per second, not English units. So you'll know as a human reader what's going on here. So we'll define so we created the dimensions. We associate those dimensions with the variable, and then we put another variable on another attribute on the variable. So now we've got all these particles, and they're not evenly distributed through the space of time. They've clumped or they've been sparse. So we'll use MPI XScan to do a sum across all the particles, and we'll know then, after we do this collectively, who has what to contribute to the collective operation. I see this pattern a lot. We'll have quite a few cases where you can't just programmatically or algorithmically say every process has 1 million bytes of data to write out. For a variety of reasons, you get imbalances, and you want to figure out, not just figure out what is going on, but you want to coordinate with everybody too. So XScan is a good case there. And after everybody knows with XScan, you'll have this my offset value, which you can then use to get your space in the variable. You count based on start and count. And then we put the variable with a collective call. Put varifloat all. We have the data array, and we have the identifier. And so there we go. That's the checkpoint. How would you restore that data? Well, we've got a couple examples online. And if you look at the PARALLEL-NETCDF quick tutorial about how you would inquire the file and check it out, I'll show you a simple one-page inquiry routine. So that way you'll sort of know how it would look. Again, we've seen this in the game of life example. We've seen a little bit of this in the Flash code, but this is going to be in this case, it's not HACC related, it's not Flash related, it's just simple look at a 2D array in a file. There's 3 steps. It's the usual MPI application, right? So I want to point out, I could fit a whole code. I'm pretty sure if I cut and paste this into a terminal and compile it, it'll run. I could fit it all in 7 lines of code plus comments. So 40 lines of commented code. We initialize MPI, we then call open with a communicator, like you saw in the game of life. Step one, inquire what is this file? Well, I made it error checking, so we know it's a NetCDF file, or NCMPI open would have failed, but we can look at the file and figure out, again, how many dimensions are here, how many variables, how many global attributes are here, and whether or not we need to deal with record variables. And with those bits of information, you can then allocate enough data structures in your code to then inquire for every dimension that we have in the file. We can figure out how long they are. Then, once we have that, we can get the variables, and then we can say something about, I have a variable x with dimensions 10 by 5, and then you can start doing stuff with that. So there are a lot of restrictions in PARALLEL-NETCDF. You have to be comfortable with dealing with multidimensional arrays. You have to be comfortable with dealing with describing your data first and then writing the data. But if you can do that, you can end up with an API that's really close to MPI-IO and hides a lot of those details. So you get pretty good performance at pretty low cost. There were some restrictions in the old days about variables being larger than 2 gigabytes, or the file being larger than 2 gigabytes and the variables being larger than 4 gigabytes. We did a lot of work to relax that in what we call a CDF5 format. And for a long time, we could say anything you create in PARALLEL-NETCDF, you can look at in serial NetCDF. And that's still true because we contributed upstream or side stream, I don't know how you can say it, to the Unidata folks, the CDF5 format. And just this summer, late spring, they released NetCDF 4.4, which in addition to writing to HDF5 or classic NetCDF formats, can also write in this CDF5 format. So even though the future is going to probably be HDF5-like file formats, we're trying to get a little more life out of the simple formats for the cases that work well for them. Just trying to think real fast if there's any points I want to make about PARALLEL-NetCDF. And you might not need PARALLEL-NetCDF. You might want to use something else. No worries, there's lots. Not only will Gerd talk about HDF5, which is a really powerful library and has a lot of great features, and a good team of people working on making those performance issues go away. You also have the Unidata NetCDF 4 folks, who I talked about a few times today already. There's a group out of Oak Ridge that did this thing called Adios, which the main selling point on Adios is you get this XML config file, and then if you find out that you want to experiment with collective I/O or HDF5 or whatever, you just tweak your config file, and the Adios API will do the right thing behind the scenes. It requires a lot less configurations and recompiling of code, was to a first order was a response to a poorly tuned MPI-IO implementation on Cray way back when, but now it's grown into its own thing. Over at Lawrence Livermore, there's this thing called Silo. They do their parallel I/O with this thing called Poor Man's Parallel I/O, which works really well for their code. They pass a baton from process to process, which sounds horrible to me, but again, pragmatic application people, they get good performance with this because you only have one process at a time beating away on the parallel file system, and they're using such large requests that that's okay. You can put libraries on top of libraries. H5Part is a particle-oriented interface. So you take the 300 some APIs of HDF5 and you introduce like, I don't know, 4 in H5Part, and you can just dump out your particle data to the file using the HDF5 under the hood, using MPI under that, using the parallel file system under that, and so you've got turtles all the way down. But it's a great example of how you can really simplify and tune for a specific domain. I keep going on this, but the point is, you might be tempted to write your own I/O library, and that would be fine, but consider the space of what's out there already. There's probably some work already done, and you can save yourself a little bit of headaches. So with that, I'm going to wrap up, and we'll break for lunch. When we come back, Gary will talk about HDF5 for a bit, Stu will talk about Globus, and Phil will talk about some of the tools we're going to use to understand these codes in the future. So we got a great afternoon coming back. I guess you can't go anywhere, so you're coming back anyway. But maybe you'll come back with some excitement versus some trudgery. I know it's been a long week, so anyway, let's go get some lunch and get some fresh air, and I'll see you back at 1, Martin?
1.
At 1, okay. Any questions before we really break? Oh, great.
So, you talked about checkpointing and restarting.
Yeah.
So sometimes we also want to save the data for visualization.
Yeah, sure.
So how would we customize the collective I/O to write a specific file format that's going to be read by the visualization tools?
Sure, there's a couple ways you might change or not change your I/O strategy if you were targeting visualization or in situ or analysis. Maybe you just keep using the checkpoint. You just checkpoint data in a way that your analysis person can look at. In the Flash case, that was a little bit overkill. They were checkpointing doubles, and they only needed single precision for their movies. And so you would want to keep as much state as possible with the double precision floating point values. But if you're going to create a movie, you would write out single precision, and that would be half the data and twice the performance and so on. What's another good example? So anyway, that's the example. You could either work directly from the checkpoint file and subset, extract a subset of data, or you might generate special data that is only useful for the visualization. That would depend on a couple different factors, I guess, how important the visualization side is and how likely you think it is that the system will crash on you. So again, the two approaches are do nothing because the checkpoint might be adequate, or you can certainly come up with a different strategy. And maybe the level of detail in the visualization code is enough. You can think of numerical methods that are resilient to errors, and so if you have less precision, maybe it takes you another couple iterations before your numerical method converges, but CPU is almost free these days, so maybe that's okay. Those are the kind of things you think about. Yeah, I think the general strategy would be the same. You're still going to try to think about the structure of the visualization needs. And one of the questions we ask people when they're trying to get an I/O problem solved is, who's using this code next? If it's only going to be checkpoint, then we can do one set of things. But if it's going to be used as part of a bigger workflow, that might change our approach a little bit. Yeah. Any other questions?
So in algorithms using mesh refinement or using like octree structures, how would you approach storing such data?
Yeah, so storing octrees and meshes is really kind of the weak spot in the I/O stack, for sure. And we've been talking about this for a decade, and it's really, I don't have a great answer for you. What I can tell you is that, for example, the Flash group, and I keep going back to them because they work half an hour from us, and two, they've been working with us for a long time, so I know their code really well. The Flash group stores the tree structure as a small variable alongside the 2D variable, and then when they restart it, they can rebuild the tree. I've got a tree that's going to be 10 levels deep, it has 100 leaf nodes, and read these blocks in and start dropping them in the tree and rebalance it and do whatever you need to do there. So absolutely, their restarting code is going to be one part I/O problem and then another part data management or data structure management problem. It'd be great if we could just restore an octree or a patch-based tree, patch-based mesh, right from the file, but we're not there yet. Other codes come up with, for example, the Chambo one is another mesh code, and they store their hierarchy in HDF5, and so the first level of the tree is a directory in HDF5, and then the second level is a subdirectory there, and so on and so forth. So again, they're reading the data from HDF5 and then rebuilding the structure as part of the restore. And so every application is doing this serialization and deserialization step on their own. In an astrophysics code that was doing octrees, yeah, again, they would take a NetCDF, parallel NetCDF variable, and the X and the Y dimension, it was 3 dimensions for space and a 4th dimension for like particle identifier. And so that's how they set up their variables. And that's unfortunately the state of the art here. So, sorry. Anybody else?
No.
Okay.
Thank you all. Let's thank our speaker.